Hi, and welcome to the video on Unit 5.3, applying the molar mass concept for mass percent and empirical formula. So these notes, by the way, will continue from your Unit 5.3 moles and mass notes. You should have, up to this point, up to the one-step mole conversions with 3 examples in your notebook. Okay, so this is another topic under moles and math. Okay, so the purpose of this is to apply the concept of molar mass to mass percent and empirical formula. So the first thing to note is that the chemical formula of a molecule shows the ratios between the number of atoms, it shows the ratios between the moles of atoms and the mass of atoms in a molecule. And what it's showing depends on the amount of the molecule that you're looking at. So if you're looking at one molecule of C6H6, which is benzene, you know that the ratio of carbon to hydrogen atoms, according to that formula, is 6 to 6. So 6 carbons to 6 hydrogen atoms. Because it's one molecule, you're counting the number of atoms. If you're looking at a mole of that substance, and remember a mole is like a dozen, then we can scale it up to mean a mole. Because if you have a mole of benzene, that means you're going to have a mole of 6 moles of carbon atoms in that benzene and 6 moles of hydrogen atoms in that benzene. So again, it's a 6 to 6 mole ratio. And if you're looking at the mass of benzene, so let's say you have 78.12 grams of benzene, which is the molar mass. That means you essentially have the mass of a mole of benzene. So you have 1 mole of benzene, you weigh it, this is the mass you're going to get, your molar mass. Well, then how much of that mass comes from carbon and how much comes from hydrogen? So 72.06 comes from carbon and 6.06 grams come from hydrogen. And we get that by multiplying the atomic or the average atomic masses by the subscripts for each element. So 6 times 12.01 and then 6 times 1.101 to get those two numbers respectively. So these ratios are not going to change no matter how much the benzene you have. I mean, even if you're looking at these numbers and you're saying, oh, that's 6 and that's moles of carbon to 6 moles of hydrogen, but here it's 72.06 grams of carbon to 6.06 grams of hydrogen. The units have changed, so of course the numbers have changed, but the ratios themselves are not going to change. So, for example, if you had 2 molecules of benzene, that means you're going to have 12 carbon atoms and to 12 hydrogen atoms. And that's still the same ratio. 6 to 6 and 12 to 12, they're the same ratios. And the reason why they're the same is because we know we can simplify a ratio. We can simplify that ratio to 1 to 1. They all boil down to 1 to 1 in this molecule. And this is known as the empirical formula. The most simplified ratios of the chemical formula is known as the empirical formula. All right, so before we go into the empirical formula, you might want to pause the video and take notes on this first half. Okay, so let's go into what the empirical formula is. Empirical formula is the smallest whole number ratio of atoms in a molecule. So essentially, the smallest or most simplified numbers you can use for the subscripts. So for example, if you're giving a molecule like C6H6, its molecular formula is C6H6, but its empirical formula is CH. And how do we get that? We get that by simply dividing out a common factor from all of those values. So we could divide out a 6 here and a 6 here because that's the least common factor there. They both can be simplified further, all right? Here in C4H8, if you look at these numbers, we can simplify this further by dividing out a 4, right? Each of these are divisible by 4, and that gives us an empirical formula of CH2. And then finally for N2O5, there's no number that we can divide these by, so this doesn't have a least common factor. The only least common factor it has is 1, so that means its molecular formula and empirical formula are the same. So we would say it has the same molecular and empirical formula. Okay, so now that we've talked about empirical formula, we're going to switch gears and talk about another topic before coming back to empirical formula. Because what we're going to do is we're going to learn how to calculate the empirical formula from the mass percent. So let's first talk about what the mass percent is. Just like any percent, it's going to be a part over the whole. So in the mass percent, it's a type of percent composition. So percent composition, percentage of what it's composed of. You would take the mass of an atom, or it could be a particle that you're focusing on. Sometimes it's not just, a single atom. Sometimes it's a moiety, like a part of the molecule, divided by the total mass times 100, okay? So in the case of mass percent of carbon in C6H6, the way that we would calculate it is we would take the mass of carbon in C6H6. So we would take their 6 carbons, and if you look on the periodic table, each has an atomic mass of 12.01 grams per mole. So 6 times 12.01 grams per mole gives us 72.06 grams of carbon. So we have 72.06 grams of carbon in a mole of carbon. And then, but the total mass of this molecule is 78.12 grams. So remember, this is the molar mass of the molecule. To get that, this molecule has 6 carbons, so 6 times 12.01, and it has 6 hydrogens, so we add the 6 times 1.01, and that gives us a 78.12 grams. And you'll notice that these are the same numbers we saw previously in the ratio. So this is how we get the mass percent. And this is getting the mass percent if they just ask you for the mass percent of carbon in a molecule. Now, they could actually give you masses of things, in which case you don't have to worry about doing these calculations. You would just take the mass of the atom divided by the total mass of the molecule that they gave you. But anyway, this is an example of how we would do that. So if you want, you can pause and take these notes now before we continue on to the next page. All right, let's look at another example of mass percent, also known as percent composition. So if we wanted to know the percent composition of sodium, carbon, and oxygen in sodium carbonate, what we would do is we would calculate, once again, step 1, calculate the mass of each element and the molar mass of the entire molecule of Na2CO3. So to get the mass of each element, we have 2 sodiums, so we're going to do 2 times 23.00. And again, these numbers come from the periodic table. Okay, the number in parentheses come from the periodic table. And that gives us a mass of 46. 1 times 12.01 gives us a mass of 12.01. And then 3 times 16, that gives us a mass of 48. So the numbers in parentheses come from the periodic table, and then these numbers here come from the subscripts. Okay. Now we're going to add all those together to get the molar mass of the molecule. So if we add these together, you're going to get 106.01. Okay, now that we have the molar mass of the molecule, to get the mass percent for each of the elements, for sodium, carbon, and oxygen, we're going to divide the mass of each element by the molar mass and then multiply by 100. So for sodium, we take the 46 divided by the 106.01 times 100, and that gives us a percent of 43.39%. That means that 43.39% of the mass of sodium carbonate comes from sodium. For carbon, it's the same thing. We take the mass of carbon in the sodium carbonate. There's 12.01 grams divided by the molar mass times 100, and it gives us 11.33%. That means 11.33% of the mass of sodium carbonate comes from carbon. And again, do the same thing for the oxygen. 48 is the mass of oxygen in the molecule divided by 106.01 times 100 gives us 45.28%. That means 45.28% of the mass of sodium carbonate comes from oxygen. All right, so if you need to, go ahead and pause the video now to copy down these notes, and then when we come back together, we'll go over the last part, empirical formula. Okay, so we can use these mass percents to get the empirical formulas. So here we have mass percents of carbon, hydrogen, and oxygen in an unknown molecule. And this is helpful because we can actually use the empirical formula that we get from this process to identify the unknown or help to prove that the unknown is what you think it is. And that's important for chemists because a lot of times when we in a lab we make something, we don't know if we have our actual molecule. So we have to do different techniques to sort of investigate our product and make sure our product is the one we want. And one of those techniques is called elemental analysis. And in elemental analysis, they basically break apart your molecule into different pieces and then determine the mass of each of the elements in that molecule and then calculate the mass percent from that. So in your report, you're going to get mass percents, and that's what these percentages are. Okay, so if you're getting these percentages and you want to figure out what's the empirical formula of this, and you're going to see if your empirical formula matches the product you want, well, the first step is to go from percent to your mass in grams. And the way that you do that is you just assume you have a 100 gram sample. So if you have a 100 gram sample, then all of these percents can translate into grams. So you just take the percent numbers and put a gram as a unit. So that part's easy. Next part is to figure out the moles for each element. So how many moles of carbon, hydrogen, and oxygen. Because remember, the chemical formula are molar ratios, right? So we look at this to get the moles of carbon. We would take our mass and divide it by the molar mass if you're using the equation. You can also set this up as dimensional analysis if you want as well, right? So remember, moles equal to mass over molar mass if you're using the equation. For dimensional analysis, you'll take your units of your given and then multiply it by the conversion factor. In either case, you're going to get, for carbon, 4.05 moles. When you do it for hydrogen, 8.20 grams of hydrogen divided by its molar mass, 1.01, and that gives you 8.12. And then for oxygen, 43.2 grams divided by its molar mass of 16.0 grams per mole, and that gives you 2.70. So now you have all of these moles. These are all moles of carbon, hydrogen, and oxygen. So we have a ratio here, except for when we write a chemical formula, we write whole number ratios. So to get them to be whole number ratios, first thing we're going to do is we're going to divide by the smallest amount. And also I should say, because this is an empirical formula, it needs to be the smallest whole number ratio. So you're going to pick the value that's the smallest moles. So carbon has a 4.05 moles, hydrogen has 8.12 moles, and oxygen has 2.70 mole. So the smallest number of moles you have here comes from the oxygen. So this is the number we're going to divide by. That means we're going to divide all of the moles, including the moles of oxygen, by 2.70 to get our smallest whole number ratio. So we divide everything by 2.70. And what we get here for carbon, we get a ratio of number of 1.5, hydrogen 3, and then oxygen 1. Okay, now last thing, we can't keep these as in decimals. Just like when you were balancing combustion reactions, we can't keep these as decimals. So you got to multiply by the smallest number possible to get them to be all whole numbers. And in this case, since the decimal that we have is 0.5, the rest of these are already whole numbers. What we're going to do is we're going to multiply everything by 2, right, to get that to become a whole number. So 1.5 times 2 gives us 3. 3 times 2 gives us 6, and 1 times 2 gives us 2, okay? So now we have our molar ratio values. So that means that the subscript in the empirical formula for carbon is going to be 3, so we get C3. The subscript for hydrogen is going to be 6, so we get H6. And the subscript for oxygen is going to be 2, that we get O2. All right, if you need to pause the video now to copy this, go ahead and do that. And then we have one more thing to go over. Okay, last thing. Now, one thing about empirical formulas is that you can have multiple molecules with the same empirical formula. So the empirical formula doesn't really identify what the molecule is. However, if you think your molecule, let's say you think your product is C6H12O4, and you look at this and say, oh, it has the same empirical formula as what I found from my elemental analysis, that's just evidence to support it, but it's not a guarantee. But there is a way to go from an empirical formula to a molecular formula. So let's talk about how we can actually do that. So to get the molecular formula, so the actual formula of the molecule from the empirical formula, what we're going to do is first determine the molar mass of the empirical formula if it's not given to you. So our empirical formula is C3H6O2. Now what I'm going to do is I'm going to get the molar mass just the same way I do it normally. So 3 times the average atomic mass or molar mass, plus 6 times 1.01, which is the average atomic mass of hydrogen, plus 2 times the average atomic mass of oxygen. Remember, all these numbers in parentheses come from the periodic table. Then I add them together and I get the molar mass of my empirical formula. Now that that's done, the next thing I'm going to do is we're going to divide the molar mass of the molecular formula, and that has to be given to you. So they either have to give you the molar mass of the empirical formula, or they have to give you the molar mass of the molecular formula, because you need one of them. In most cases, it's the molar mass of the molecular formula that will be given to you, but not always. But generally, they give you this one. So they'll give you that number, and then what you're going to do is you're going to divide the molar mass of the molecular formula by the molar mass of the empirical formula that you just found. So let's say they tell you, oh, the molar mass of the molecular formula is 148 grams per mole, and you found the molar mass of the empirical formula to be 74.06 grams per mole. So what you're going to do is you're going to take the 148 grams per mole divided by the 74.06, and that's going to give you a number of about 2. You're going to round it. If it's completely off, then you might want to check your math, but usually the numbers are going to be close to some whole number. All right, so once you have this number, then what you're going to do is you're going to take all the subscripts in the empirical formula and multiply it by that value which you get, which is essentially your least common factor. So I multiply the 3 by the 2, the 6 by the 2, and the 2 by the 2, and that gives me a molecular formula of C6H12O4. Oops, sorry. All right, so that is it for this video. If you need more time to copy the notes, please pause and do so. And other than that, have a quality day.